Swayam Prabha. Digital India. Educated India.
Difference between the initial and final values decays with time. Okay, so you have the final value plus any difference that was there between the final and initial values will decay with time. So that's one way to interpret this. We do all of this so that it turns out that for the step-like inputs for first order systems, after enough practice, you will be able to simply look at the circuit and write the response. Okay, of course, you need a lot of practice to do this. Initially, you should do it systematically, but you should be able to do it after a while. And this part, of course, is the final value. So this Vc of t, in general, this turns out any V of t in a first order system, and by the way, it could be I of t also, any current as well. Okay, I have demonstrated this with the capacitor voltage in a particular circuit, but it turns out that any branch quantity, either voltage or current, in any first order circuit can be represented in this form for a step input. Okay. So this is V final plus V initial minus V final times exponential. It is minus t by RC, but to make it more general, I will write minus t by tau, where tau is the time constant. Okay. So this is the general form, and like I said, exactly the same holds for a current as well. I final plus I initial minus I final exponential minus t by tau. Okay. So I hope this is clear. In fact, you would have seen this type of formula, but it has some basis. Essentially, what it says is that it expresses it as the final value plus the difference decaying over time. Okay. Now we also had expressed the expression in a slightly different way. Vc of t is Vp 1 minus exponential minus t by Rc plus Vc of 0 exponential minus t by Rc. Okay, it's exactly the same expressions, but divided differently. Okay, as 0 input and 0 state responses. So now, again, writing it in a more general form, V of t would be V final 1 minus exponential minus t by tau plus V initial exponential minus t by tau. Okay. So compared to the previous expression, this gives you a slightly different interpretation. Okay, exactly the same final solution, of course, but only the interpretation is different. Here you think of this as this term building up to the final value. That is, if you just look at this part of it, it starts from 0 because 1 minus exponential is 0, and then it builds up to V final. Okay, and this you can think of as any initial condition that is there on the capacitor decaying with time. Okay, so at t equal to 0, you will only have the initial part and it decays with time. Okay. So this is yet another interpretation. You can think of the total response as one part, which is building up to the final value, and another part, which is the initial part decaying with time. And like before, this also holds for currents. Okay, we will quickly take some examples and see. So this also holds for currents. Okay. So with this, you should be able to write down the step response of any first order circuit. We will also take examples of circuits with inductors. Okay, and evaluate the step response without necessarily having to go through the differential equation. Okay. Now, as usual, in the beginning, when you are not very fluent with this, I would recommend writing down the differential equation, identifying the terms properly, and then writing down the solution. As you get more and more practice, you should be able to do this more conveniently. Okay. Now, to be able to do this, we have to identify. There are three quantities in this. Okay, three things we have to identify. That is V final or the final value, V initial or the initial value, and also the time constant tau. Okay, so we will see how to do this. Now the time constant is the same for a given circuit regardless of which quantity you pick. Okay, for instance, let me take the same example. RC, and let's say that this has an initial condition of Vc of 0, and the input steps from 0 to Vp at t equal to 0. Okay. So now we have been looking at Vc of t. What I would like you to do is to give me the expression for IR of t, the resistor current. Please try to do this. Please calculate the expression for IR of t, the current in the resistor. Yeah, I have got a response that says it's Vc of t by R. That is not correct because the voltage across the resistor is not Vc of t. Okay. So please try to do this. Give me the expression for IR of t. Obviously, one way to find the current is to find the voltage across the resistor and divide it by R. Alternatively, you recognize that the current through the resistor is the same as the capacitor current, and if you know the capacitor voltage, you should be able to calculate the capacitor current. Okay, you can do it either way. Okay, I think there are a number of responses. Clearly, the voltage across the resistor is given by Vp minus Vc of t. Okay, so IR of t is Vp minus Vc of t divided by R, which in turn can be written as Vp minus Vc of 0 divided by R exponential minus t by Rc. Okay. So again, you see this exponential minus t by Rc appearing in the expression. Okay. And also, let's try to relate it to the initial and the final condition. Okay. First of all, if the initial voltage across Vc is Vc of 0, then the initial voltage across this R, okay, so let me write it like this. VR is in this direction. So VR initially would be, or let me write the IR directly. So I initial is, when I say initial, it is just after the step is applied. Okay. So it is Vp minus Vc of 0 divided by R. Okay. Now a useful special case to consider is when Vc of 0 equals 0. In that case, you know that the capacitor voltage is 0 initially. The input voltage here jumps up. The capacitor voltage cannot change. So the voltage across R will be equal to Vp. That's what we see, right? If Vc of 0 is 0, the initial current is Vp by R, and that's what will charge the capacitor. We also saw that that will be the slope of Vc, that will be related to the slope of Vc. Okay? And what is I final? Okay? I final is, what does it mean to have a steady state in a circuit with capacitors and piecewise constant voltage? Steady state means that the voltages in the circuit will be constant with time. Okay. So if the capacitor voltage remains constant with time, then there is no current through the capacitor, so it's like an open circuit. So clearly the current through the resistor is the same as the current through the capacitor. Okay. So I final will be equal to 0. And you again see that whatever we have here, this response conforms to the general formula, which is I final plus I initial minus I final exponential minus t by tau. Okay. Because I final is 0, we have only this part is not there, and we have only this part. Is this okay? So every quantity, I mean, this is a very simple circuit, but every quantity will correspond to, will conform to a formula, this or this. By the way, these two formula are the same. The only difference is the terms are grouped differently and interpreted differently. That's all. Okay? Is this fine? Now we should also try and see how to evaluate the initial and the final conditions by looking at the circuit. Okay? Let me first take the final condition. The final condition is after the steady state is reached, and a steady state, because we are looking at constant inputs, means that all voltages are constants. Okay. So now if a capacitor voltage is constant, any capacitor voltage, it means that the derivative is 0, and that means that the current is 0. Okay, the current through the capacitor is 0. Now, if the current through the capacitor is 0, that means that it can be replaced by an open circuit. Okay. Okay. So you replace the capacitor by an open circuit and find the quantity, whichever quantity is of interest to you. Okay. So this is how we would find the final value. Let's do it for the case we took. This is our circuit RC, and let's say I am interested in the capacitor voltage VC. Now to get the final value, what I would do is to open circuit the capacitor, that is, the capacitor is not there. So clearly the voltage that appears here equals Vp, and this would be the final value. Okay. Now this circuit is very simple, but the same principle applies to all the circuits. Similarly, let's say I am interested in the resistor current, then again I will take the case of input stepping from 0 to Vp. To calculate the final value, I open circuit the capacitor. Okay, and clearly this current would be 0. Okay, so this current would be 0, and that indeed is the final value of IR. Okay, we'll take a slightly more complicated example later. Okay, so is this part clear? Any questions about what we discussed so far? What we did was to extend our discussion from last class. There we had mathematically evaluated the solution to the differential equation. Now here what we have done is to identify certain characteristics of the solution to first order system with a step input, and we can use those characteristics directly to write down the solution with a little bit of experience. Okay. So if you have any questions, I will take them now. Okay, it appears that things are clear. So finally, we have to identify the time constant. Okay. So there is a question, but it looks like it's incomplete. I'm not able to understand the question here from LG Industries. We also have to identify the time constant that I will come to later. In case of our circuit which has only R and C, it's very easy. So let me call this Vs. So first of all, you deactivate the source. Sources. Okay. Then determine the resistance across the capacitor. Okay. And finally, let's say the resistance is R in this case. And finally, the time constant tau will be R times C. Now this is very simple and silly for this case because we have only R and it's very obvious what the resistance across the capacitor is. Okay. When I say across the capacitor, what I mean is between these two terminals. Now this principle applies even to very complicated circuits as long as you have only one capacitor. Let's say I have a circuit with a number of resistors and I will show only the capacitor like this connected to terminals 1, 1 prime. I also have a number of sources. I will show one example here. Okay. So now what I have to do to find the time constant is, first of all, I null this circuit. That means that any independent source is set to 0. If it's a current source, it's an open circuit. If it's a voltage source, it's a short circuit. And I have these two terminals 1, 1 prime across which the capacitor is connected. So what I have to do is to determine the resistance of this circuit looking into 1, 1 prime. Now this we have done many times, right? It's basically the Thevenin equivalent resistance looking into the terminals 1, 1 prime. Okay. So this RTH is what we have to determine, and once we do that, the capacitor value is C, the time constant tau will be given by RTH times C. Okay. So you can very easily verify that it's true for our very simple circuit. Looking between these two terminals to the left side, we have only R. But even if you had a very complicated circuit, it would be true. You would have to find the equivalent resistance looking this way, and the time constant would be RTH times C. Okay. Is this clear? So we know how to find the final value and we know how to find the time constant. Okay. We also have to find the initial value. When I say initial value, it will be just after the step is applied. Okay. That also we will proceed to do. So if you have any questions, please interrupt. I am not getting many questions today. So that means that either you are understanding everything or probably understanding nothing. So if If you're understanding everything, it's good, but if you have difficulty understanding something, please ask the questions on the chat window and I'll answer them. So RTH is a notation I use for the Thevenin resistance looking into 1 prime. Okay. So if you have a circuit with two terminals 1 prime, then when you deactivate the circuit and find the resistance, that is the Thevenin resistance across those two terminals. Okay. So that is RTH. Okay. So now we have to find the initial condition. Okay. Again, I am talking about the initial value of any variable, not just the capacitor voltage. Okay. There is another question, can we use RL network for this? It's not clear to me. Are you talking about circuit with resistors and inductors? Yeah, the same principle applies. I will come to those examples a little later. Okay. Exactly the same principle applies because with a single inductor, it is also a first order circuit. Now let me look at how to calculate the initial condition or the initial value.